Hello, this is a physics video on refrigerators. I've been following now for about 10 years Young and Freedman's University Physics, and we're in chapter 20, which is on the second law of thermodynamics. We've done videos on heat engines, which basically use heat to produce work, like a steam engine, or an internal combustion engine. We had a video on internal combustion engines. And so in this video, we're going to look at refrigerators. Refrigerators are basically heat engines working in reverse. And so instead of adding heat and using that heat to do work, refrigerators remove heat and throw it away. Anyway, so you might remember a diagram written like this, and my own hand, but it went the other way. And so you're in your heat engine, you have the heat that comes to some, this is where the engine takes place. The heat engine is the circle in the other video. And so the heat produces work, and the work comes out. And then you have some residual heat that's discarded. That's the heat loss. Now it works the other way with a refrigerator. With a refrigerator, we start with something cold. Note the colors: blue for cold and red for hot. So a refrigerator extracts heat from something cold and then throws it outside, inside the refrigerator, outside the refrigerator. And of course, this works for air conditioners too, inside the house, outside the house. But of course, this won't happen on its own. There is no such thing as a refrigerator that doesn't need a workless refrigerator. Doesn't exist. You're going to have to input work in order for this to happen. Because things go from hot to cold. They don't go from cold to hot. And so the very idea, I mean, it's genius, this invention of pulling heat out of something that's already colder. Wow, that's just brilliant. What a wonder we live in this world that we live in. Okay, so this is kind of the heat diagram in reverse. So refrigerators are heat engines working in reverse. Where have I heard that before? So a heat engine the heat engine that we've done a video already on has a net output of work. It gives off work. It drives automobiles. But a refrigerator won't work unless we put work into it. It's going to have to take work for this thing it's like going uphill, getting the heat that's in the refrigerator out of the refrigerator. That's going to take work. Now, in a heat engine, the kind of amount of discarded heat is negative because it's a loss. But for a refrigerator, the heat that's coming out of the, say, refrigerator, or coming out of the room that you're air conditioning, that's going to be positive heat that's put into this process. For a heat engine, the Q heat is positive because it's heat coming into the system. But for a refrigerator, we're throwing that heat outside. Whatever body we're trying to cool. So things are kind of in reverse. And so, by the way, whether you're dealing with a heat engine or a refrigerator, the absolute value of QH plus the absolute value of QC plus the absolute value of the work, this equation works for all the absolute values, whether you're a heat engine or a refrigerator. But for a refrigerator, the amount of heat that's given out is the sum. The heat that you're throwing outside the house from the air conditioner, or the amount of heat you're throwing outside the refrigerator, that Q hot heat is going to be the sum of the amount of heat you're pulling out of the refrigerator or pulling out of the house, which is positive in this case, plus the amount of work that you're putting in for that thing to happen. Okay, so we have a spec called a coefficient of performance. That's how well we're doing with this sort of thing. And so the coefficient of performance is going to be, and it's a dimensionless number. So it's not joules, it's nothing like that. It's just a pure number. And the coefficient of performance is going to be the absolute value of the amount of heat you're pulling out divided by the amount of work it takes to pull it out. And so that's what this coefficient of performance is. And since work is Q hot minus Q cold, I know you get what I'm saying, is work, we can also put it in this kind of form as well. Okay, so how does a refrigerator work? By the way, I apologize, I can draw better than this, but it is what it is. You get the picture, right? So the compressor is where the work is done. The compressor is plugged in. You know, it's a motor, and what the compressor does is it takes, and of course there's some sort of a working substance in this thing, maybe Freon or something like that. So there's some sort of a chemical, a vapor. It could be a vapor, something in vapor liquid equilibrium most of the time. The compressor pulls it out of, say, the fridge or the room if it's an air conditioner, and it compresses it. It makes it go to high pressure. And of course, as pressure goes up, pressure and temperature are proportional. So as the pressure goes up, the temperature goes up, and the volume goes down. This is called a condenser. And this is on the outside of the fridge or on the outside of the house if it's an air conditioner, right? And so you have this heat that's being given off. And then when it comes back in, you have an expansion valve. What happens when the volume goes up? When the volume goes up, the pressure goes down and the temperature goes down. And so we have a lower temperature coming into the fridge. So the condenser that makes it high pressure on the outside is the hot part. And the evaporator that is when it's expanded at a lower temperature and a lower pressure, that's the evaporator. Okay, so that's kind of the refrigeration cycle, how it works. And this is how it works for refrigerators. This is how it happens for air conditioners and so forth. Okay, now coefficient of performance in an air conditioner. Okay, so H in the context of an air conditioner, AC, is the amount of heat pulled out of the house, for example, out of the room or whatever, the amount of heat pulled out divided by time. How much heat is removed per time? That's H. Now, we know that power is work per time. So if we go back to the coefficient of performance, the coefficient of performance really was, remember, was the absolute value of QC over the absolute value of work. Well, we can multiply both sides by T, and we have QC equals HT. And then multiply both sides by T, and we have work, W equals PT. T's cancel out, and so we basically know that with an air conditioner, the coefficient of performance is the rate of heat removal divided by the amount of power that is going into the compressor, basically. Okay, so this is a formula for the coefficient of performance that relates especially to air conditioners. Now, air conditioners often have an energy efficient rating, or an EER, when you get a air conditioner. Now, from a science standpoint, it's a mixed unit. So it's like BTUs per hour per watt. Well, these units do not match. A watt is a standard unit. BTU is a British unit. It's not an English unit. It's not the scientific unit standard usually. So basically, if you do the conversion, the EER rating is going to be 3.414 times larger than the coefficient of performance that we might prefer in physics. Well, we're almost done with this video, believe it or not. So there's also something called a heat pump. A heat pump does the opposite of air conditioning. It takes the heat from the outside and brings it in. And so it cools the outside, as it were. I mean, not much, because the world is just too hot. Cools the outside, but heats the inside by pulling the heat in. Well, this has been a video on refrigerators. Go thou and be cool, since it is the summer of 2020. It was 89 degrees in New York today, and so I'm glad that I have an air conditioner. Have a great day until the next video.